than the space physiology lecture. So today we will learn the concept of hyperbarism. What do we mean by this term hyperbarism? Then we will learn what is nitrogen narcosis and what are the effects of oxygen and carbon dioxide toxicity. So these are the three learning objectives for our today's session. So let's begin. So in this figure you can see the atmospheric pressure versus the pressure represented in millimeters of mercury at various levels of depth. And in the first column, the water level or the sea level depth is given in meters. So this is 0 meter, that is the sea level. So at sea level, the atmospheric pressure is 1. So when we say the atmospheric pressure at sea level is 1, this 1 atmospheric pressure is equal to 760 millimeters of mercury. So 1 atmospheric pressure is equal to 760 millimeters of mercury at sea level. So when we go deep, for example at 10 meters, this is atmospheric pressure 2, and you can see the pressure in millimeters of mercury, it has risen from 760 to 1520. So it has doubled. Similarly, if we go deeper and deeper till 90 meters of depth, this is 10 atmospheric pressure, and the figure you should remember is 7600 millimeters of mercury. So at sea level, 1 atmospheric pressure is equal to 760 millimeters of mercury, and at 90 meters deep, this will be equal to 10 atmospheric pressure, which is equal to 7600 millimeters of mercury. Now this is the elaborated form of the same description. You can see 3 columns. Depth in meters as well as in feet is given in the first column. Second column shows the atmospheric pressure, and the third column here represents the volume change in liters. So at sea level, we have discussed the atmospheric pressure is around 760 millimeters of mercury. Now this 760 millimeters of mercury is equal to 1 atmospheric pressure. Similarly, at the depth of 10 meters, which is equal to approximately 33 feet, the atmospheric pressure has doubled from 1 to 2. However, you can see the volume of the gas has been compressed to half of its original value. So suppose the original value was 1 liter at the sea level. Now this volume has been compressed to half of its original value at atmospheric pressure 2. Similarly, if we go deeper and deeper at 20 feet, 30 feet and 40 feet, you are increasing the atmospheric pressure and the volume of the gas is decreasing progressively. Now this is the diagrammatic representation of the same concept. You are going deep into the sea. This is the sea level here. This is equal to 1 atmospheric pressure. So at sea level, the atmospheric pressure is 1. Now this 1 atmospheric pressure is equal to 760 millimeters of mercury. So remember this figure, 760 millimeters of mercury, which is equal to 1 atmospheric pressure. Now what we have done here is we have placed a bell and we have submerged it into the sea. So as we go deeper from the sea level to around 33 feet, where 33 feet is equal to atmospheric pressure of 2. So you are increasing the atmospheric pressure. You are increasing the atmospheric pressure by going deep into the sea. On the other hand, the volume of the gas has been compressed to half of its original value. So suppose the original value was 1 liter earlier at the sea level. Now this is 0.5 liter or half a liter. Similarly, if we further go down at approximately 100 feet, which is equal to 30 meters. So at 30 meters, the atmospheric pressure is around 4. So you can see the volume of the gas has been further compressed to 1/4 of its original value, and it can be compressed to 1/8 of a liter at the depth of 233 feet. So what does this show? This is the representation of the Boyle's law. So I hope you remember the Boyle's law. You must have read in your physics lectures in FSC. What is Boyle's law? Can anyone from the student tell me what is meant by the term Boyle's law, named after Boyle, scientist? Yes. Anyone? PV is equal to K. Okay. Anyone else? Boyle's law. Yeah, you are right in a way. Boyle's law. Okay. Pressure volume product is always constant. Okay. Yes, you are right. Excellent. So inverse relationship is there. Inverse relationship between what? Inverse relationship between pressure and volume. If you increase the pressure, you are going deep into the sea, and as we go deep into the sea, we are increasing the pressure. So increase in the pressure will have an opposite effect on the volume. So pressure has an inverse relationship with volume. So inverse relationship of pressure with volume. So you increase the pressure, you will observe a parallel or progressive decrease in the volume of the gas, and the temperature should be kept constant. According to the Boyle's law, pressure is inversely proportional to the volume of the gas at constant temperature and constant conditions. So if you go down deep into the sea, you are increasing the pressure. And as we increase the pressure, you can observe progressive compression of gas. So the value which was 1 liter at the sea level, it has compressed to 1/8 of its original value at 233 feet. Again, this is this representation of the same thing. This is the 0 meter or the sea level, and as we go down, as we go deep into the sea, you are increasing the pressure. So if you increase the pressure, you will compress the volume of the gas, as you can see by the volume of this balloon or bubble. This indicates compression of the gas. So the size of the balloon or the bubble was much larger at the sea level than at suppose 1000 meters. So you can easily compare inverse relationship between pressure and volume of gas at constant condition, and this is known as Boyle's law. Understood? Should we proceed? Ji beta. Should we move on? Okay, fine. So a frequent terminology that has been used is hyperbarism. So what do we mean by this term? If we break this term into two, hyper means excessive, barism from pressure. So excessive pressure, hyperbarism, increased pressure. So How do we increase the pressure? So when we descend into the sea, obviously we are increasing the atmospheric pressure. The external pressure is increasing. So to prevent the lungs from collapsing at these high pressure conditions, the lungs, they tend to collapse. So to prevent the collapsing of lung, air must be supplied at very high pressure so that the lungs do not collapse. And this maneuver exposes the pulmonary blood to extremely high alveolar gas pressure, and we call it as hyperbarism. In simple words, this means increased pressure. So when you descend deep into the sea, you are exposing yourself to extreme degrees of high pressure. So under that condition, the lungs, they tend to collapse. So to prevent the lungs from collapsing, air must be supplied at very high pressure, and this maneuver is known as hyperbarism. And beyond certain limits, these high pressures can cause serious physiological changes which can sometimes lead to fatal consequences. And what are the effects of hyperbarism? We will learn two important effects of high partial pressure of gases on the body. The first effect is known as the nitrogen narcosis. You must have read this term, nitrogen narcosis. And the second effect is known as oxygen toxicity. So these are the two most common effects of high pressure of gases, especially during deep sea diving. So we start with the nitrogen narcosis first, then we will discuss oxygen toxicity, and at the end of the lecture we will learn what is meant by carbon dioxide toxicity. So first we start with the nitrogen narcosis. What is meant by the term nitrogen narcosis? And the French naval officer Jacques Cousteau, he was the one who wrote the book The Silent World, and he used the term rapture of the deep. Rapture of the deep. What is meant by rapture of the deep? What do we mean by the term rapture? Yes, you can check your dictionaries. Rapture means, yes, students? No, this is not rupture. No, this is rapture. Rapture. Rapture means sense of extreme pleasure, sense of extreme joy. So, uh, Cousteau termed nitrogen narcosis as the rapture of the deep. It is also known as the Martini effect, right? Martini effect. Why we call it as the Martini effect? Anyone? Any guess? I know you all watch movies. What is meant by the term Martini effect? Any wild guess? No one? Okay. Martini is for the cocktail martini. It also gives feeling of immense pleasure, immense joy. So nitrogen narcosis, known as rapture of the deep or the Martini's effect, right? So what do we mean by the term narcosis? Narcosis in simple word means a state of unconsciousness, semi-consciousness or stupor, right? Stupor refers to lethargy or suppression of all the sensations. So when all the sensations are suppressed, when all the feelings are suppressed, the person is said to be under stupor or narcosis. So when the effects of nitrogen produces narcotic effect, especially during deep sea diving, we will label it as nitrogen narcosis. So nitrogen narcosis means the narcotic effect produced by nitrogen at high pressure. Remember, this is under extreme degrees of pressure, especially during deep sea diving. So this is known as nitrogen narcosis. So what happens during nitrogen narcosis? Why there is feeling of immense pleasure? Why there is altered sensorium or altered mental state similar to alcohol intoxication? So the symptoms are very similar to alcohol intoxication. That is why it is known as that is why it is known as Martini's effect. So breathing compressed air is very essential for deep sea diving. So nitrogen, you all know, is an inert gas. What do we mean by the term inert gas? Yes. What is meant by the term inert? Inert gas? Yes, students. So nitrogen is, yes, unreactive. Yes, nitrogen is an inert gas. It does not react with any other gas. So it does not produce any effect at the normal atmospheric pressure. There is no effect of nitrogen at the sea level. But when a person breathes pressurized air during deep sea diving, then the narcotic effects they begin to appear, and this will cause altered sensorium, altered mental state, similar to alcohol intoxication. So the effects are very similar to alcohol intoxication. That is the reason we can call it as the Martini effect, and Jacques Cousteau termed this as the rapture of the deep or the rapture of the depths, right? So this is meant by the term nitrogen narcosis. Now, what are the effects of nitrogen narcosis? What are the different symptoms? So, initially the symptoms are very mild. As we go deep into the sea, suppose this is 0 meter or the sea level. So, if we go deep around 120 feet, so symptoms of joviality appears. Joviality means cheerfulness, happiness, right? Rapture of the deep, remember? And around 200 feet, the person becomes very drowsy, and around 250 feet, the person becomes very clumsy, and the strength begins to wane. And at depth of greater than 250 feet, this is very critical, the person becomes almost useless, inability to perform any physical activity, inability to perform any cognitive function as well. So both the physical and the cognitive skills are lost at 250 feet. So the initial symptoms are very vague, very mild, but if you go deeper and deeper, greater than 250 feet deep, this is very critical. The person becomes useless. The person is unable to think, unable to perform any physical activity. Now this graph is very important. Uh, in fact, this is three graphs merged in one. So if you focus on the red curve, can you spot the red curve in the middle? This is the oxyhemoglobin dissociation curve. And I hope you remember the oxyhemoglobin dissociation curve, because to understand the concept of oxygen toxicity, now we are going to discuss the concept of oxygen toxicity. You must understand the oxyhemoglobin dissociation curve. We are done with the nitrogen narcosis. Now we are going to start oxygen toxicity. And for that, you must understand the concept of the oxyhemoglobin dissociation curve. Do you remember the oxyhemoglobin dissociation curve? Only then you will be understand the concept of oxygen toxicity. Should we revise the oxyhemoglobin dissociation curve and then start the oxygen toxicity, or should we move on straight away? What do you say? Because to understand this curve, you must have a strong grip on the oxyhemoglobin curve. So I'm waiting for your answer. Should we discuss oxyhemoglobin dissociation curve and then you discuss this graph, or what? Okay, right. So if you focus on the red curve, this is the oxyhemoglobin dissociation curve, and this is the same curve that we have discussed already. Do you remember this graph, students? Do you remember this graph? This is the oxyhemoglobin saturation curve or the oxyhemoglobin dissociation curve. So this is very important, and this is modified from your textbook. I have modified some things from the graph given in your book. for the purpose of explanation. Here you can see the partial pressure of oxygen on the abscissa given in millimeters of mercury. On the ordinate axis we have hemoglobin saturation given in percentage form. And on the opposite side, the volume percentage is given as well. So remember, when you are supposed to draw oxyhemoglobin dissociation curve, the students, they tend to forget this part, the volume percentage. For some reason, the students skip this part and they only mention the PO2 versus hemoglobin saturation. So I request the students, please do not miss the volume percentage. This is important as well. This is very important, in fact. So any graph without its unit, without its axis is useless. So you must denote the graph with proper axis. X-axis we have partial pressure of oxygen in millimeters of mercury. On y-axis, on one side, left-hand side, you can see hemoglobin saturation in percentage. On the right-hand side, you can see the volume percentage. Now this volume percentage can be expressed in milligrams per deciliter as well. We will discuss that later. So this is the sigmoid curve. Can you spot the red sigmoid curve? S-shaped curve, and it starts from the partial pressure of 0. So when the partial pressure of oxygen in the blood is around 0 millimeters of mercury, obviously 0% of the hemoglobin is saturated. What do we mean by hemoglobin saturation? Anyone? What do we mean by saturation of hemoglobin? How does hemoglobin get saturated? Anyone? Any idea? Oxygen binding. Okay. So we all know there are 4 subunits for oxygen. You all know the 4 subunits of hemoglobin. And for the saturation of these 4 subunits of hemoglobin, 4 molecules of oxygen are required. Right? So 4 molecules of oxygen, they are required to saturate all the 4 hemoglobin subunits to 100%. Right? If 2 out of 4 hemoglobin subunits are saturated, this will be 50% saturation. 50% saturation means only 2 subunits are saturated with oxygen, 2 are unsaturated. Similarly, if 3 out of 4 subunits are saturated, this means 75% of the hemoglobin is saturated. 3 out of 4 hemoglobin subunits are saturated with oxygen. This means the hemoglobin is saturated till 75% value. So this is meant by the term hemoglobin saturation. That is the reason we can also call this curve as oxyhemoglobin saturation curve. Right? And another important concept is to understand the P50 value. This is the P50 value. What is meant by the term P50? Yes, you have already discussed this. Please hurry up. What is meant by the term P50? Yes, students. P50 means this P represents the partial pressure of oxygen. Capital P denotes the partial pressure of oxygen, and 50 stands for the hemoglobin saturation. So the partial pressure of oxygen at which 50% or half the hemoglobin is saturated is the P50 value, right? The partial pressure of oxygen at which half the hemoglobin is saturated is the P50 value. Here you can see the hemoglobin saturation. This shows the 4 subunits of the hemoglobin. Here you can see hemoglobin is partially saturated, again partial saturation, 3 out of 4 subunits are saturated with oxygen. One is still missing. One oxygen molecule can still bind here. So this is 3 by 4 or 75%. So saturation is 75%. And this is 100% saturation. Here is the 100%. All the 4 subunits are saturated with oxygen. These blue dots, these are the oxygen molecules. So all the slots are filled. This is 100% saturation. And this is 3 over 4. 3 out of 4. One slot is still missing. So 3 by 4 or 75% saturation. So what is meant by the term? P50, the partial pressure of oxygen at which half of the hemoglobin becomes saturated is P50. So what is half of the hemoglobin? Here, this is the 50% saturation. So if you trace this 50% saturation, this will approximately be equal to 25 millimeters of mercury. So the P50 value, remember that the P50 value is 25 millimeters of mercury. So when we say P50 of 25, this is the normal value. So at 25 millimeter partial pressure of oxygen, half of the hemoglobin is saturated. This means 2 of the subunits are saturated. Not shown in this figure. At 50% saturation, this will be 2 out of 2. 2 saturated and 2 unsaturated. Did you get the concept of hemoglobin saturation? Ji beta? So that we can move on. Have you understood the concept of hemoglobin saturation? Okay. So P50 is the partial pressure of oxygen at which half of the hemoglobin is saturated and normal value is around 25. In some books it is written 27 millimeters of mercury, but according to your textbook it is around 25 millimeters of mercury. So the P50 is around 25. And this is the sigmoid curve. Why the curve is sigmoid in shape? If you observe closely, there are two components of the curve. One, the initial component is the steep component. Here you can see the steep portion. And the latter half of the curve is flat. Can you observe the two components? The steep portion and the flat portion. From 60 to 90 millimeters of mercury, this is the partial pressure of oxygen where the curve is almost flat or almost parallel to the horizontal. And this portion of the curve is known as the loading zone of the oxyhemoglobin dissociation curve. This is the loading zone. What do we mean by the loading zone? By loading zone, we mean oxygenated blood leaving the lungs. Oxygenated blood leaving the lungs. So there is loading of oxygen. Oxygen is leaving the lungs, and the other portion, the steep portion, this is the venous blood where the reduced blood returns from the tissues. So this is the unloading zone. So the blood leaving the lungs is the arterial blood, and the blood returning from the tissues is the mixed venous blood. So the flat portion is the loading zone, where loading of oxygen takes place, and the steep portion of the curve is the unloading zone where oxygen is unloaded from the tissues. And if you focus on the right hand side of the y-axis, the volume percentage is given, and it is given from 0% till the value of 20. So 20 is the upper limit of the curve. So any brilliant mind who can tell me the oxygen binding ability of hemoglobin? What is the normal value of oxygen binding capacity of hemoglobin? Anyone? Okay, let me rephrase the question. Let me rephrase the question. The question is 1 gram of hemoglobin can bind or can carry how much volume of oxygen? So this is the question, right? Uh, no, better. The question is, Malaika, the question is 1 gram of hemoglobin can carry how much volume of oxygen? Anyone else? This is the oxygen binding capacity or the oxygen carrying capacity. No matter how the unit can be in millimeters in mercury, Farhan. Volume of gas is represented in milliliters or liters. The question is 1 gram of hemoglobin can carry how much volume of oxygen? Yes, this is very close, 1.39 milliliter. This is almost very close to the correct value. This is 1.34 milliliters, beta. 1.34 milliliters. So remember the value. This is the oxygen binding capacity of blood, or the oxygen binding capacity of hemoglobin rather. So 1 gram of hemoglobin has the ability to carry 1.34 milliliters of oxygen. And what is the hemoglobin content in an average healthy adult male? Anyone? अरे बेटा जल्दी बताइए. What is the average hemoglobin concentration in a healthy adult male? What is the average hemoglobin concentration? 13 to 17. Again, no units. What is the unit? Any value without its unit is useless. No, that is not the correct unit. Yes, grams per deciliter. Grams per deciliter. This means 1 gram of hemoglobin, 1 gram of hemoglobin has the ability to carry 1.34 milliliters of oxygen. And the normal concentration of hemoglobin in adults is around 15 grams per deciliter, where 1 deciliter is equal to 1 deciliter is equal to deciliter means 1/10 of a liter. 1/10 of a liter is equal to 100 milliliters, right? So we can also write the unit as grams per 100 milliliter. So both the units are correct. 15 grams is the average concentration of hemoglobin. 15 grams per deciliter or 15 grams per 100 milliliter. So if 1 gram can carry 1.34 oxygen, how much 15 gram will carry? That is the question. Now do the math. Hurry up. Yes. If 1 gram can carry 1.34 milliliter of oxygen, how much oxygen will be carried by 15 grams? 15 grams per deciliter is the average concentration in healthy adult male. So this is around 20. So 19.6 or 20. This is the volume percentage. Can you see the upper limit of the curve? This is the upper limit of the curve, around 19.6 or 20 milliliter, or we call it as the 20 volume percent. We call it as 20 volume percent. So we can express this milliliter unit into volume percentage, right? So I will repeat the concept. There are two portions of the hemoglobin oxygen hemoglobin dissociation curve. The initial portion is the steep portion, and the latter half is the flat portion. From 60 to 90 partial pressure of oxygen, the curve is flat, and this is the loading zone where oxygen is leaving the lungs, and the steep portion is the unloading zone where blood is returning from the tissues. So this is venous blood versus the arterial blood. Then we discuss the concept of P50. P50 is the partial pressure of oxygen at which half of the hemoglobin is saturated. So when two of the subunits are saturated and two subunits are unsaturated, this will be 50% saturation. And the partial pressure at which 50% of the hemoglobin becomes saturated is 25 millimeters of mercury. And this 25 millimeters of mercury is the normal P50 value. And then we discuss the concept of oxygen carrying capacity of hemoglobin, where 1 gram of hemoglobin can carry 1.34 milliliter of oxygen. And in a normal healthy adult male, 15 milligram per deciliter is the hemoglobin content, which can carry 20 volume percent of oxygen. Right? Again, you can see the concept of hemoglobin saturation. So why the curve is sigmoid or S-shaped? What is the physiological advantage of this S-shaped curve? So this is one of the Viva questions. Why the curve is sigmoid and what are the physiological advantages of this sigmoid shaped curve? So there are three physiological advantages of this sigmoid shaped oxyhemoglobin dissociation curve. Number one, it allows greater oxygen uptake. Despite the great variation in the alveolar PO2, the oxygen uptake is much greater. So this is the first advantage. Second advantage, the tissues are supplied with oxygen according to their needs. When oxygen is required by the tissue, it will be immediately supplied. And when no more oxygen is required, no oxygen will be supplied to the tissue. And this mechanism is known as the buffer mechanism of hemoglobin. Remember, hemoglobin by itself acts as a buffer. It will dissociate oxygen only when it is required. This is the indigenous ability of hemoglobin, the ability to provide oxygen to the tissues only when needed. So these are the three advantages of the sigmoid shaped curve, and the phenomenon is known as positive cooperativity. Remember the term positive cooperativity from cooperation. And what is positive cooperativity? Anyone? जी बेटा आंसर मैं दे चुका हूँ. What is positive cooperativity? No one? So, so I'll give you a hint. Positive cooperativity is related to the hemoglobin saturation. Uh, no, beta. Positive cooperativity means that the saturation of hemoglobin progressively increases. The hemoglobin saturation occurs in a stepwise fashion. For example, when one oxygen molecule binds to the hemoglobin, its affinity for further binding of oxygen increases. So it will bind this with the second oxygen molecule. When the second oxygen molecule binds with the hemoglobin, now the affinity of this hemoglobin for oxygen further increases. And this is known as the positive cooperativity. That is why the curve is sigmoid shape. So progressive increase in the affinity of hemoglobin for oxygen is known as the mechanism of positive cooperativity. So what are the clinical significances of the P50 value? So what is P50? P50 is the partial pressure of oxygen at which half of the hemoglobin is saturated, and the normal value is around 25 millimeters of mercury. So when we say the P50 value is greater than normal, what do we mean by the term P50 value greater than normal? This means that the affinity for hemoglobin, the affinity of hemoglobin for oxygen is decreased affinity of hemoglobin with oxygen. So when the affinity is decreased, this will shift the curve to the right side. So rightward shift will take place when there is increase in the P50 value. So when you increase the P50 value, you are decreasing the affinity for oxygen, and vice versa. When the P50 value is less than normal, this means the affinity of hemoglobin for oxygen is greater, and this will shift the curve to the left side. So what are the factors that shift the curve to the right side? What are the factors that shift the curve to the left side? And the easiest way is to remember this mnemonic. I will write it down for you. The mnemonic is C beat. C beat. B E A T. C beat. So C beat will shift the curve to the right. So for rightward shift, C beat. Remember the mnemonic. For rightward shift, C beat, where C stands for carbon dioxide. So if you increase the partial pressure of carbon dioxide, the curve will shift to the right side. B stands for bisphosphoglycerate. The complete name is 2,3-biphosphoglycerate, bisphosphoglycerate, diphosphoglycerate. All are the names of the same thing. And this E stands for what? Anyone? Yes, we have discussed this. What are the other factors that shift the curve to the right side? Ji beta. This is frequently asked university question. Frequently asked university question. This E stands for exercise. So exercise is another physiological factor that shifts the curve to the right side. And what does this A stand for? A for acidity. A for acidity. Acidity means increase in the hydrogen ion concentration. So increase in acidity or increase in hydrogen ion concentration, or you can say decrease in the pH value. It means the same thing. So if the pH value falls, the oxyhemoglobin dissociation curve will shift to the right side. So A for acidity or A for altitude. This A also stands for altitude. So higher altitude will shift the curve to the right side again. And what does this T stand for? T for temperature. So increase in temperature, increase in body temperature will again shift this oxyhemoglobin dissociation curve to the right side. When we say the curve is shifting to the right side, this means the P50 value is increasing. Remember that. When the curve shifts to the right side, this rightward shift will increase the P50 value as well. So when the P50 value increases, it will be easier for the tissues to extract oxygen. And what are the factors that shift the curve to the left side? Students, are you with me? Ji beta, students, are you with me? Are you getting this? This is very important. Ji beta. Okay. So we have discussed the factors that shift the curve to the right side. Now, opposite of all these factors will shift the curve to the left side. Opposite of this. So if you decrease the partial pressure of carbon dioxide, if you decrease the levels of 2,3-bisphosphoglycerate, if you decrease the temperature, if you decrease the acidity or increase the pH, decrease acidity or increase in pH, all these factors will shift the oxyhemoglobin dissociation curve. Another frequently asked viva question is the effect of fetal hemoglobin on oxyhemoglobin dissociation curve. So how does fetal hemoglobin will affect this oxyhemoglobin dissociation curve? Anyone? whether hemoglobin F will shift this curve to the right side or to the left side. Anyone? जी beta. What will be the effect of fetal hemoglobin on this oxyhemoglobin dissociation curve? These are the effects of hemoglobin A, adult hemoglobin. What will be the effect of hemoglobin F on this curve? Will it shift the curve to the right side or to the left side? Or will there be no effect? These are the only three possibilities. Either it will shift to the right or left, or no effect at all. Ji beta. Anyone? Right side, Khadija Javed. Anyone else? Ji. What will be the effect of hemoglobin F on this oxyhemoglobin dissociation curve? Khadija says it's right side shift. Anyone else? So do you all agree with her? Okay. So you agree with her. So Farhan says to the left. Hmm. Anyone who says no effect at all? Hmm. Leftward shift. Okay, beta, the answer to this is shift to the left side. Why fetal hemoglobin will shift the oxyhemoglobin dissociation curve to the left side? Because of increased affinity. Yes, that is the answer. Fetal hemoglobin has far more affinity for oxygen than adult hemoglobin. So when the affinity increases, remember that when the affinity for hemoglobin to oxygen increases, it will shift the curve to the left side. So you have understood the oxyhemoglobin dissociation curve, everyone? Can we come back to this curve where we left? Ji beta. Now you are fully aware of the concept of oxyhemoglobin dissociation curve. So we can come back to this curve. And this is the extended or the modification of the same oxyhemoglobin dissociation curve. Can you spot the red curve in the middle? This red curve is the oxyhemoglobin dissociation curve. Here you can see the partial pressure of oxygen in millimeters of mercury, right? Partial pressure is given on the x-axis, and this is the same volume percent. Remember the volume percent, the oxygen carrying capacity of hemoglobin. 1 gram of hemoglobin carries 1.34 milliliters of oxygen, and 15 grams of hemoglobin will carry 20 milliliters of oxygen, and we will call it as 20 volume percent. So volume percent is on the y-axis. Now this oxyhemoglobin dissociation curve has been modified. This is the extended version. Why this is the extended version? Because in the previous graph, the partial pressure was given till the value of around 100 or 120 millimeters of mercury. Here you can see the extension from 760 to till 3000 millimeters. So this is the extended version of the same oxyhemoglobin dissociation curve. We have extended the PO2 value from 100 to 3000, right, in millimeters of mercury. So you can see the steep portion initially and the flat portion, the latter half of the oxyhemoglobin dissociation curve is the flat portion. Remember the loading zone and the unloading zone. The flat portion is the loading zone and the steeper part is the unloading zone. So this is the oxygen hemoglobin dissociation curve in red. And there's a curve inferior to it is this green curve. This is the dissolved hemoglobin. This is the dissolved hemoglobin. This green curve is the hemoglobin in dissolved state. The red curve shows the hemoglobin bound to oxygen. The green curve shows the hemoglobin in dissolved state. And the blue curve, the uppermost curve, it shows the total oxygen in blood. This is the total oxygen in blood. So both dissolved state and bound state, they are added, and this is the aggregate curve. The blue curve is the total oxygen. So you can see the oxygen binding with hemoglobin in the red curve, the oxygen in the dissolved state in the green curve, and the total oxygen in the blue curve. Are you with me, students? Ji beta, are you with me? There are three curves. The red curve shows the oxygen bound to hemoglobin. The green curve shows the oxygen in the dissolved form, and the blue curve is the total oxygen. Sum of red and green is the blue curve, right? So what is the normal volume percentage? This is 20 volume percent. Remember, 1 gram of hemoglobin can bind to 1.34 milliliters of oxygen, and normal hemoglobin concentration is 15 grams per deciliter. So this means 15 multiplied by 1.34 will give you approximately 20, and this 20 volume percentage is the normal oxygen carrying capacity of blood, right? So this is the oxygen bound to the hemoglobin, right? Oxygen bound to the hemoglobin. So in a normal oxyhemoglobin dissociation curve, there is no contribution by the oxygen in the dissolved state. I repeat, in the normal oxyhemoglobin dissociation curve, there is no contribution of dissolved oxygen. But we have extended this curve from 100 to 3000 millimeter mercury. So this is the extension of the previous curve. And this green curve shows that 9 volume percentage is the contribution from the dissolved oxygen. So 20 volume percent by the oxygen bound to hemoglobin, and 9, can you trace it? This is 9 volume percent by the dissolved state. Remember, there is no contribution by the dissolved oxygen in the normal oxyhemoglobin dissociation curve. And you can see till the level of around 100 here, suppose this is 100, almost no contribution by the dissolved oxygen, almost no contribution. But at 3000, there is contribution of around 9 volume percent, right? So if we add this 20 and 9, this will give you the total oxygen. So 20 plus 9 will give you 29. So this point A is the point of total oxygen utilized. Total oxygen bound to hemoglobin as well as the oxygen in the dissolved state at the pressure of around 3000 millimeters of mercury. So this is the volume percentage at the pressure of 3000 millimeter of mercury. So the PO2 is around 3000, and the volume percent has increased from the normal 20 to 29. And from where this extra 9% came from? From the dissolved state. So this point A is the total oxygen, which includes not only the oxygen bound to hemoglobin but also oxygen in the dissolved state. So if we move to the left side towards point B, this is point B. If we move to the left side, you can observe a progressive fall in the volume percent, and the fall is around 5%. So 29 minus 5 will give you the value of 24 volume percent. Now this is the venous blood at the tissue side. So at the tissues, the oxygen has been dissociated, and that is the reason we see a fall in the volume percentage. So this is the unloading, right? And the normal value for this quantity is approximately at the partial pressure of around 1200 millimeters of mercury. So this is the effect of oxygen toxicity. So this shaded region gives you the partial pressure of oxygen where the oxygen becomes toxic. The oxygen becomes toxic. Here you can see this area whole is the area of oxygen toxicity. And what is oxygen toxicity or oxygen poisoning? This is the last slide. When the oxygen content in the tissues is increased way beyond its normal value, and when the pressure is as high as around greater than 2 or sometimes 3 atmospheric pressure, known as hyperbaric oxygen, this will give the toxic effects of oxygen because the limit is only 1.34 ml. This is the oxygen carrying capacity of blood or the hemoglobin. You cannot exceed this limit. This is the cutoff point. So if you increase the pressure, you will observe, you will experience the toxic effects of oxygen, and these are the effects of pulmonary edema, increase in the metabolism, increase CNS symptoms like irritability, muscular twitching, dizziness, sometimes convulsions or coma may be there, or if the atmospheric pressure is around 5 atmospheric pressure or 4, this may lead to fatal consequences. So these are the effects of oxygen toxicity when the pressure is much higher than normal. Remember, the oxygen carrying capacity of hemoglobin is limited to 1.34 ml per gram. 1 gram of hemoglobin can carry only this much oxygen. No matter how much the atmospheric pressure, you will not be able to exceed this cutoff value of hemoglobin. So this is all for today. Today we discussed the concept of hyperbarism. We discussed the concept of nitrogen narcosis, and we discussed the concept of oxygen toxicity, focusing on the effects of oxygen toxicity on the
सर टाइम हो
oxyhemoglobin
गया,
dissociation curve. All
डॉक्टर
right,
याद
we will
करें.
resume from here. Thank you very much. Allah Hafiz.